So besides the things that we were just talking about, that some things are soluble and some are insoluble, you can cause things to be more soluble or things to not be soluble. Like if you think of dissolving something, you probably know that if you heat up a solution, you're probably going to be able to get more to dissolve, right? So we're going to talk about that. We're also going to talk about what affects nonpolar things to dissolve in things, not just ionic compounds dissolving. So one other factor that should be taken into account whenever you're dissolving something is how disordered a system is. So this is called entropy, and this is something we'll talk a lot more about in Chem 162. But things are favored to be more disordered. It is easier to have something disordered than ordered. So like if you think about your bedroom, right? It's very easy for things to become disordered. It actually takes work to order them. So disordered things are more favored. So that is something that also plays into the solubility of certain products, but again, not something we're necessarily going to focus on. That's more of a Chem 162 principle. So the one thing that we will be using quite a bit is polarity. So if something is polar or nonpolar, that affects if it's going to be soluble or not. So when we're trying to dissolve covalent things, and the phrase, and yes, we use this in chemistry, is like dissolves like. So that means that polar will be soluble in polar things and non-polar things will be soluble in non-polar things. Polar things and non-polar things do not mix well. So that's why oil and water don't mix together. Well, yes, they do have different densities. So a lot of the times people will be like, oh, well, oil is less dense. That's why it's on top. Well, yeah, that's why it's on top, but why don't they mix together? And the reason they don't mix together is because oil is very non-polar. If you kind of zoom in on this molecule here, you'll see that it's a whole bunch of carbons and hydrogens, and it's very symmetrical. This is a non-polar molecule, whereas we know that water is very polar. So they do not like to mix together. Okay, so like dissolves like. Again, also those intermolecular forces are going to play into solubility, London dispersion forces, dipole-dipole forces, hydrogen bonding, and ion dipole, all of which we have talked about before. So again, like dissolves like, and that's really kind of the most important thing to remember. Okay, so we're going to talk about dissolving molecular or covalent things in water, and again, that has to do with polarity. When water has hydrogen bonding, so it's really polar, it will dissolve molecular compounds that also have hydrogen bonding or that are also polar. So if I'm looking at these two molecules here, CH3, CH2OH, you should notice I've got an OH here. That means it can do hydrogen bonding. So this thing is probably going to be soluble in water. So water, polar hydrogen bonding, this also polar hydrogen bonding. Now this molecule here, and I would draw it out for you, it looks like this. It is polar, right? So this would be soluble in water as well because it's not symmetrical, but there's no hydrogen bonding because you don't have your hydrogen actually bonded to the oxygen. So this one's a little less polar, but it's still polar. So it would dissolve. This one would just dissolve better in water. Okay. The other things that kind of affect solubility are the size of molecules. So if I have this like really big molecule, and anytime you see these like big long chains of carbons and hydrogens, that part is nonpolar. Remember, carbon and hydrogen have very similar electronegativities. This is very symmetrical. So this part of the molecule would be nonpolar. But if you'll notice, there's an OH over here. So this can do hydrogen bonding. So the bigger these molecules are, if you have a much larger nonpolar part, this hydrogen bonding over here isn't going to matter as much. So if it's large and nonpolar, it's not going to be very soluble. So even if it can do hydrogen bonding, the bigger nonpolar part you have, it's not going to be as soluble. So an example of these polar and nonpolar things being soluble in water or not are vitamins. Okay, so you might have heard of water-soluble vitamins and fat-soluble vitamins. Some dissolve better in water because they're polar, and some dissolve better in fat because they are nonpolar, and fat is a nonpolar molecule, and that's how they move to different parts of your body. So vitamin B over here, this is vitamin B, and this is vitamin D. Vitamin B over here has a whole bunch of polar groups. So you'll notice these are not just carbons and hydrogens. We got a bunch of nitrogens and oxygens in all of these groups, which are really electronegative elements. I've got a phosphate group down here, a hydrogen bonding here. All of these polar groups make vitamin B polar on the outside. And so it's actually very soluble in water. So it can move through water or aqueous parts of your body. Whereas vitamin D, notice these are all carbons and hydrogens. And anytime you see these lines, that's just a bunch of carbons and hydrogens. The only part of vitamin D that's polar is this little one down here that, yes, it can do a teeny bit of hydrogen bonding, but this part is so big that overall it's non-polar. So this is going to be a fat soluble vitamin. So vitamin D actually has to move through fat molecules. Okay, so in example number 1, it says which of the molecules below is a water soluble vitamin and which is fat soluble. So I want you to look for those groups, which I've kind of already circled for you, and determine which one would be polar in water versus polar soluble in fat. Right, so this one over here, a bunch of carbons and hydrogens. Notice there is one little polar group here, but this part is much bigger. So this is going to be your fat soluble one. Whereas over here, I have a bunch of oxygens and OHs where I can do hydrogen bonding. This is going to be your water soluble molecule. So this is a question I could ask you based on structures. Alcohols also, so alcohol just means it has an OH group on it. These are these molecules I've been talking about, right, that have OHs. The bigger they get, and they only have one OH, this is actually going to be mostly non-polar. So you'll see this other word meaning kind of soluble, and it's miscible. You can kind of think of it as mixable if you can't really remember what it means. Miscible just means they will mix. So things that will dissolve are miscible or will mix together. So methanol is small and has hydrogen bonding, so it is miscible in water because it's polar. The bigger the molecules get, you look down here at pentanol, yes, it does have an OH, so it can do one little hydrogen bond over here, but the rest of the molecule is very non-polar. It is not going to be miscible in water, or very, very low mixability or miscibility. It is going to be mixable in a non-polar solvent. Remember the whole like dissolves like thing? Hexane, C6H14, is just a bunch of carbons and hydrogens. So that is a non-polar solvent, and this is going to be more miscible in that. So the more polar things are going to be miscible in water. The more non-polar things are going to be miscible in a non-polar solvent, something like hexane. Okay, so polarity really also plays into things being soluble or not.